The curve C has parametric equations x equals sine 2 theta and y equals cosec to the power of 3 theta. Find an expression for dy over dx in terms of theta. So what we need to do is we need to find out dx and dy for both of these. So to start off, we're going to take dx of d theta for this one, and that will be 2 cos 2 theta as we bring the 2 in front, and sine differentiated is cos. So now we're going to do y equals cosec to the power of 3 theta. This will be dy over d theta equals 3 cosec squared theta equals minus cosec theta multiplied by cot theta, and we can just expand this, which is minus 3 cosec to the power of 3 theta times cot theta. And to find dy over dx, we just do this dy part over this dx part, and that's the answer. Hence, find the exact value of the gradient of the tangent 2c at the point where y equals 8. So we know that cosec to the power of 3 theta equals y, and if this is y and this is the point where y equals 8, we just sub in 8, and then we do this to the cube root to get cosec on its own, which equals 2, and cosec is equal to 1 over sine theta, so we can do 1 over sine theta equals 2, and then multiply it on both sides, and a bit of rearranging will get you 1 over 2 equals sine theta, and then we just do the inverse of sine 1 over 2, which gives us pi over 6, and then using this dy over dx equation from before, which is the gradient, we do pi over 6 where theta is, which will give us this, and then when we expand it, it will give us this. So we can do minus 24 root 3, and this 2 times half will just give 1. So you will get minus 24 root 3, and that is the answer of the gradient. The curve C1 with parametric equations x equals 10 cos t, y equals 4 root t sine t, meets the circle C2 with the equation x squared plus y squared equals 66 at 4 distinct points as shown in figure 2 here. Given that one of these points S lies in the 4th quadrant, find the Cartesian coordinates of S. So this is the 4th quadrant here, 1, 2, 3, 4, and it's asking us to find out where the points meet. So all we need to do is we've got our values for x and y, and we just need to plug these into this equation as done here, and this is 10 cos t squared plus 4 root t sine t squared equals 66, and as you can see, the centre is just 0, 0, so it's just x squared plus y squared. And if we expand 10 cos t squared, we can do 100 bracket cos squared t, and we can use the identity 1 minus sine t squared, ignore that, to expand it so that everything is in terms of sine t, and this will give 100 minus sine squared t, and then for 4 root t sine t squared, it will be 32 sine squared t, and then you just add these, so 100 minus 100 sine squared t plus 32 sine squared t equals 66, and then we'll just rearrange this. And doing that will get you minus 68 sine squared t equals minus 34, and then sine squared t equals 1 over 2 as we divide minus 34 by minus 68. So sine t equals plus minus root 2 over 2. And as S is in the 4th quadrant, y is negative and x is positive. This is really easy to see as we go here, this is positive x, and down here it is negative y. So this will be negative. X equals 10 cos t, so we need to find out the value of cos t. So we can do this by doing cos squared t equals 1 minus sine squared t. We know what sine is, so we know what sine squared is, so we just do 1 minus half, which gives us half, and cos t equals root 2 over 2. So we put that back into this equation. Root 2 over 2 times 10, cancel out the 2, is 5 root 2. Y equals 4 root 2 sine t, so we put sine t back into that, which gives us 4, as this cancels out, and this cancels out, and you get 2 times by 2, which gives 4. And again, like we said earlier, as it is in the fourth quadrant, y is negative, so this becomes minus 4. This should also have been minus. And these are our coordinates, 5 root 2 and minus 4. The curve shown in figure 3 has parametric equations x equals 6 sine t, y equals 5 sine 2t. The region R, shown shaded in figure 3, is bounded by the curve and the x-axis. Show that the area of R is given by pi over 2 and 0, 60 sine t cos squared t dt. So the first thing we do is we use x equals 6 sine t, and we find out the value of it differentiated, which is 6 cos t. Okay, so when t is 0, 6 sine 0 is 6. And when t is pi over 2, 6 sine pi over 2 equals 6. So we know our limits are 0 and pi over 2. And then we can just do this as the area, x times y, 5 sine 2t times by 6 sine t dt. And if we expand that, it will give us 30 sine 2t cos t. And as we know, sine 2t from our double angle formulae is 2 sine t cos t, so we can put that back into equation. 30 times 2 sine t cos t times cos t will give us 60 sine t cos t squared, and that is the answer. Hence, show by algebraic integration that the area of R is exactly 20. So this is our equation, and we'll set u as cos t and minus du as sine t dt. So this part. And then we can take the 60 out of the equation and rewrite it like this, and then plug these back in. So we get u squared from the cos squared times minus du, which gives us, if we integrate it, u cubed over 3 times by minus 60, as this is just like minus is taken here, which equals minus 20 u cubed. And as u equals cos t from earlier, we can do minus 20 cos cubed t. And then if we put this back into here, we can just plug in these values. So minus 20 cos to the power of 3 pi over 2 minus 20 cos to the power of 3 t in brackets 0. And as cos pi over 2 equals 1, as cos pi over 2 equals 0, 0 to the power of 3 times minus 20 is going to be just 0. And here, as cos 0 equals 1, 1 cubed is 1, multiplied by minus 20 gives minus 20, and we do the upper limit minus the lower limit, so 0 minus minus 20 gives 20, and that is it. A curve C has parametric equations x equals 3 plus 2 sine t, y equals 4 plus 2 cos t. Show all points on C satisfy y equals 6 minus x minus 3 squared. So to do this, we need to first get rid of this cos 2t using our double angle formulae, which is 1 minus 2 sine squared t. And then we can rewrite this y equation as 4 plus 2 bracket cos 2t, which gives us y equals 6 minus 4 sine squared t. And then for x, we write it as 3 plus 2 sine t, and we can rearrange it to get sine t on its own, which will be we minus 3 on each side and then divide it by 2, and this is sine t on its own. And then we put this value of sine t back into this equation, y equals 6 minus 4 brackets this sine t squared, and then we can just expand that, and we get 4 on each side. So this is 4 multiplied by this, so we can literally just cancel these out, and it will simply be 6 minus x minus 3 squared, and this is the answer. Okay, sketch the curve C. Explain briefly why C does not include all the points of y equals 6 minus brackets x minus 3 squared. So to sketch the curve C, we obviously know that from this equation from before. If you expand it, you'll get a minus x squared because of this minus here. So there'll be a downward opening parabola, which basically means it is shaped like that. The highest point is at 3 and 6, as this x is 3 and this y is 6. And the range of sine t is minus 1 to 1. So all we need to do to find out the ranges of x is we do x equals 3 plus 2 sine t from the last question, and then we sub in these values of sine t. So for sine t equals minus 1, which is the lower sort of limit, x equals 1. And we can see this from 3 plus 2 times minus 1, which gives us 1. And when sine t equals 1, x equals 5, as it is 3 plus 2 times 1. And then for the range of cos 2t, it is also minus 1 and 1, so y ranges. And using our equation from the last question, we can put these limits back into the formula, and we get cos 2t equals minus 1, y equals 2, and when cos 2t equals 1, y will equal 6. And we know this from this part, as the highest point is at 6. So our coordinates will be 1 to 2, 5 to 2, and 3 to 6. Now we need to sketch this curve, so using this we can just do 1, 2, 5, 2, we can do 3, 6. And then we just connect these using our downward parabola. Sorry, it's a little bit wonky, but yeah, this is 1, 2, 5, 2, and 3, 6. And explain briefly why C does not include all points of y equals 6 minus x minus 3 squared. So as we can see from these parts of the question, there is the parametric equations involve sine and cosine, so they are trapped between minus 1 and 1. So x can never be less than or greater than 1 and 5, as seen from here or here. So it can't include all points of this as it is trapped. The line with the equation x plus y equals k, where k is a constant, intersects C at 2 distinct points. State the range of values of k, writing your answer in set notation. So this all follows on from our question before, and obviously this is the equation from before as well. And we can just rewrite this in terms of this equation. So y equals 6, blah, blah, blah. So you put x plus this part of y equals k. And then we can obviously expand this, so it becomes this. And then we can just rearrange it until we get this equation here. And then we bring this all to one side, so we plus x squared minus 7k and plus 3, and it gives us this. And now we need to find the discriminant, which is b squared minus 4ac, and we need to set it equal to 0 to find the tangent limit. So essentially this means the point at which the line intersects the curve once, because this is the limit. This is where we need to find out what the highest value of k can be before it hits this limit where it only intersects C once, and here we need it to intersect twice. So To do this, we just find out what a, b and c are. A equals 1, b equals minus 7, c equals k plus 3, and then we just put them back into this equation. And we get 49 minus 4k plus 12, which simplifies to 37 minus 4k equals 0. And then we find 4k equals 37, and then k equals 37 over 4. So at this point, the line intersects a curve once, so k is less than 37 over 4. To find the lower value of k, we basically need to find out the lower limit. So we get this equation again, and we use the values from last time of the coordinates. So we've got 1 and 2, and k will equal 3 using this equation. 1 plus 2 equals 3. And similarly, using 5 and 2, we get k equals 7. Now, to work out which value we need, we realise that this equation can be rearranged to give y equals minus x plus k. So that is an indication of what the line will look like. So essentially the line will be going down like this, as the gradient is minus 1. So when we have our equation here, and we've got the point 1 and 2, if the line is hitting it and going this way, and the curve is going this way, it will only hit it once. Whereas if the curve hits it at 5 and 2, it can hit it twice. So in this scenario, we would pick k equals 7 as our lower value of k. And obviously, as it is can apply to this situation, k can equal 7 and be greater than it. So we would write it as 7 is less than or equal to k, which is less than 37 over 4.